In this lecture, I want to continue the discussion of the determination of lags in dynamic models. And essentially what I want to do is to look at a number of different procedures that have been proposed for tackling that problem. And first of all, I want to look at the armor type of model. So that we have the autoregressive moving average model, say with the autoregressive component of degree P and the moving average component of degree Q, and write that in what I hope is relatively familiar notation. So that we have the autoregressive polynomial in the lag operator L phi P, and the moving average polynomial in the lag operator theta of L. Or alternatively, we can move to the ARIMA type of model where we've introduced differencing, either the straight differencing or seasonal differencing, so that we could consider a model where we have all those parameters to determine empirically from the data, and the model is now phi of L and then phi capital P of L to the power S, where S is the period of seasonality, so that if we're dealing with quarterly data, S would be 4. We then have delta S, and that's the seasonal difference, raised to the power D, straight delta raised to the power small d, all applied to our original series yt as being equal to still the moving average component theta, then the seasonal moving average component, and the white noise error term. And the problem that I'm looking at today is that of determining the orders of the polynomials in models of this type and similar models, so that in this context we want to determine empirically the values of small p, capital D, small d, capital Q, and small q. One method that's been proposed for determining those parameters empirically is that associated with Box and Jenkins. And first of all, you would use delta S, the seasonal difference, and the straightforward first difference to render the original observed series yt stationary. So we use these differences to ensure that the resulting variable, which will be delta S to the capital D, delta to the small d, yt, is stationary as far as we can tell. And we check that by looking at the parallelogram for this difference series. Having done that, we look at the parallelogram for the difference series, and from inspection we want to identify the values of the remaining parameters. At this first stage, we've now determined the 2D parameters. What we have to do now is determine the autoregressive parameters, the straight autoregressive small p, the order of the seasonal autoregressive capital P, and similarly for the moving average orders. So that inspect the parallelogram for And let's now denote by yt star, that difference variable. And from that, we identify P, capital Q, and small q. And at that point, there is quite an element of subjective judgment in choosing those parameters. Having done that, we would estimate the model for those values, which we'll now denote by the hats. So estimate the model for P hat, D hat, D hat, Q hat, and Q hat. And I don't propose to discuss the estimation, whether that's least squares or full likelihood. Finally, we would engage in diagnostic checking. In other words, we're now asking the question whether, in fact, the model we chose in the combination of step 1 and step 2 is the appropriate model for this data. And we can divide the diagnostic checks into two categories. First one, which in this particular context is usually one particular test statistic, namely the box and Pierce Q statistic, which would be T sigma j is 1 to H, say R j hat squared, and where R j hat is the jth serial correlation coefficient of the residuals from the model estimated at stage 3. So that's from the residuals theta t hat. And use the result that asymptotically the Q would be distributed as a chi-squared on the null hypothesis that the errors epsilon t are white noise, with degrees of freedom given by H minus, and then in effect, the number of parameters we've had to estimate. And so that means all the P's and all the Q's and in this model. So that's minus the P, P, Q, Q. And that's just used as a portmanteau test statistic of the hypothesis that, in fact, the residuals epsilon in the model that we've estimated are estimates for a white noise error process. Notice that for that particular test, there's no specific alternative. We're specifying what the null is, that the errors epsilon are white noise, but the alternative is any form of serial correlation. The other form of diagnostic checking could be what's called overfitting of the model, and that is increasing the values of P, P, Q, and Q, estimating the model for those larger values of those parameters, and then performing a test of significance on the additional included coefficients in the model. Well, that's a very quick, stylized presentation of the Box and Jenkins approach to modeling ARIMA processes. The details are much more complicated, and you can hedge many of the statements with careful expressions which allow for certain problems which we know will arise. But in general, that is the approach. Well, what problems would you expect to arise in that approach? Well, first of all, the first step where we difference the series may not be appropriate. And in particular, if we're thinking of yt as being an economic time series, as soon as we introduce some differences and then start modeling the differences using autoregressive moving average processes, the implication is that either that variable doesn't have an equilibrium solution or its equilibrium solution is zero. Or putting it another way, all we're doing is modeling the short-run behavior, but you can't, from this single equation to explain the single economic time series, have an equilibrium solution within it, other than zero. Well, that needn't be such a major drawback in this univariate context of ARIMA models, because all we need to do is subtract the mean from yt. And we could just then say that the mean is in fact the equilibrium value. But when we come to models where we're not just relating a single time series yt to error processes, but a particular time series to another set of time series and errors, that particular point is much more important, that you would like to have a long-run equilibrium solution which makes sense economically, and not just having either a constant term being that long-run equilibrium solution or a long-run equilibrium solution of zero. Another problem that can arise is that all we're doing at stage one is looking at the correlogram for yt, and if that appears to be the correlogram for a non-stationary series, differencing it, and then look at the correlogram for that difference variable, and continually increasing the order of differencing until the correlogram looks as though it's the correlogram of a stationary series. So it's quite possible we make mistakes at this stage, even if differencing is appropriate. And therefore it's possible that we over-difference at that first stage. If we over-difference, what are the implications? Well, the implications are that the resulting error process is now certainly a moving average error process, but a moving average error process with a unit root. In particular, if, say, the true model didn't have any differencing at all, but it did have autoregressive and moving average components, let's say that's the true model, or alternatively, if we want to abandon true as being non-operational, we'd have to say that this is the model which gives us the best representation of the process generating the data. Then if we over-difference and introduce delta yt so that we only modeled delta yt, then this would correspond to modeling an equation of that type. And given that this is the true model or best model, the implication is that e to t is in fact the first difference of epsilon t. Now, if in estimation of this model we were able to spot that the autoregressive part here and the moving average part of the representation on the right-hand side had this common root, or this common factor of 1 minus L, then there would be no problem. We would have spotted that redundant common factor and identify the true model. But in practice, if we were estimating this model, then we're quite likely to run into computational problems, because we know that the true model is one where there is a moving average error component here with a unit root, and to estimate moving average error processes with unit roots is quite complicated, and you can use up lots of computer time because of the difficulties of converging when the true root is unity. So that it's quite likely at that stage you wouldn't estimate a unit root in the moving average of the error process, and therefore not identify this redundant factor of delta. In fact, Sargan, in a paper looking at overdifferencing and moving average error processes with unit roots, has been able to show for simple models like this that asymptotically the probability of estimating a unit root when the true model does have a unit root is in fact 0.673. I don't wish, again, to go into the details of that because it involves a great deal of complicated algebra. But mention that just to illustrate the point that it's quite likely in practice, if you have estimated this model when that's the true one, you won't in fact find that common factor of delta. So that's one problem that does arise with this first stage, the differencing. It's quite easy to get the differencing wrong. What about the second stage? Well, it's certainly easy to get the choice of all these orders of the polynomials wrong at the second stage. Very easy indeed. But the beauty of this approach is that we have the fourth stage, which is the diagnostic checking. So even if we do make a mistake at the second stage, we would hope to pick it up at the fourth. So the whole question is, how powerful is the diagnostic checking at the fourth stage? So that if we do make a mistake at the second stage, are we likely to find it at the fourth? And unfortunately, the answer in general is that the fourth stage isn't very powerful in picking up misspecifications. And if we look at the approach for the diagnostic checking using, for example, the Q statistic of Box and Pierce, in a simulation project at LSE, Marriott in 1976, and this work is referred to in the discussion of the paper by Prothero and Wallace, on modelling macroeconomic time series in the Journal of the Royal Statistical Society, Series A, 1976. Marriott did a simulation study of the performance of the Q statistic. And one of the most important findings in that simulation study was that the probability of type 1 error empirically was very much smaller than the nominal probability of type 1 error. So that if you took the critical values from, say, the chi-squared distribution at the appropriate degrees of freedom for 5% significance level, what Marriott was finding is that the statistic, in fact, would have had a probability of type 1 error much less than 5%. As a consequence, you're going to reject restricted models much less frequently than you believe you are, because the empirical size of the test is less than the nominal size. The confidence intervals will be larger, and so you will reject the restricted models less frequently than you believe you would. And that's consistent with the results in the literature that when people have estimated time series models, and in particular Prothero and Wallace, when they were estimating the univariate ARMA and ARIMA processes for the econometric model they were looking at, when they used the Q statistic, it was very rare for this to indicate misspecification. It was always accepting the restricted model that had been estimated at stage 3 and identified at stage 2. Further work on the Q statistic by Davis, Newbold, and Triggs in 1976 which is at the moment an unpublished paper from the University of Nottingham, but will be published within the next 6 months. And they looked at this same problem, the power and the size of the Q statistic, and with a combination of analysis and simulation, came to the conclusion that in fact the probability of type 1 error, empirically determined, is in fact about a quarter of the nominal probability of type 1 error. So it's confirming the results of Marriott, but they're now putting an order of magnitude on the difference between the empirical size and the nominal size. So insofar as the diagnostic checking is done using the Q statistic, it's very likely that you're not going to find misspecification at the second stage. What would happen if we were doing the diagnostic checking via overfitting? Well, first of all, we would expect that this performs better, because in fact what we do here is now consider a specific alternative which has some of these values larger than the ones we've chosen initially. We then estimate that more general model and test the significance of the extra coefficients. And that testing could be done using a likelihood ratio test, for example, because we have now estimated both the restricted and the unrestricted model. And therefore we would probably expect this approach to have quite good power, at least asymptotically. Well, there are in fact problems with that approach as well. And the first one is that in overfitting you must be careful not to introduce the reverse sequential testing procedure, in that you start off from the first identified model, you then consider whether you ought to increase the values of any of these parameters and estimate that model. If at that stage you come to the conclusion that you should have done, in other words, you've rejected the hypothesis that the extra included coefficients are 0, you might then perform yet another overfitting test by increasing the values of the P's and the Q's even further. And if you don't reject that increase in the values of P and Q, you may continue. And what in effect that sequence of tests is doing is performing the reverse sequential testing procedure, and reverse in the sense that it's the opposite to the optimal one of Anderson. What are the consequences of using the reverse procedure? Well, the first obvious point is that with that procedure you don't need to specify what the maintained hypothesis is at the beginning. It only needs to be the most general model that you didn't have to consider, so that you perform a series of significance tests, and the maintained is the last most general model that you didn't need. So that for that reason alone it's very difficult to work out the power of the procedure. Another point is that in doing that sequence of tests, the test statistics are not independent of each other. And therefore, if you were trying to do this sequential testing in a reasonably systematic way, and in particular trying to control the probability of type 1 error for that sequence of tests as a whole, because the test statistics are not independent, it's very difficult to work out what the probability of type 1 error is for the sequence of tests as a whole. And one way around that would be to use Bonferroni intervals. And so we set a bound on the probability of type 1 error for the sequence of tests as a whole, rather than fixing that probability. But as I mentioned in the last lecture, the result of that is that the Bonferroni intervals are larger than the intervals you would have if you'd been able to calculate exactly what the probabilities of type 1 error are for each of the individual tests. And the consequence of that, again, is that it's going to be more favorable towards the restricted hypotheses. So that if you do overfitting, and you do a series of overfitting tests, then that's analogous to the reverse sequential testing. And if you do try to control the probability of type 1 error via the Bonferroni intervals, the consequence is that, again, you're going to reject restricted models much less frequently than you would if you were able to evaluate the exact probabilities of type 1 error. So again, that approach is biased towards accepting this model rather than the more general models that you're just considering. And finally, if in fact, when you're doing the overfitting, you happen to choose an alternative model which is the true one, even in situations like that, the power to detect the true model can be quite small for certain ranges of the parameter space. And this is a point that's been made by Hendry in a paper given at the Federal Reserve Bank in Minnesota in 1975, with the title on time series on the time series approach to econometric modeling. And what he showed there was for a particular example, namely an ARMA 1-1 model, yt is equal to delta yt minus 1 plus epsilon t plus alpha epsilon t minus 1. Which has the autoregressive part stationary and the moving average satisfying the invertibility condition. That if this is the true model, but in fact at this stage you choose the wrong model to estimate, and in particular if you chose a first order autoregression instead of the first order autoregression with first order moving average, you estimate that model and then use overfitting to check whether that's the appropriate model. Now, even if you're fortunate enough to choose this model as the one to compare the estimated model with, so that in your overfitting you are fortunate in choosing the true model, there's a very wide range of the parameter space for delta and alpha where that test has got low power. And in particular, for sample sizes of 40, when delta was 0.8, there was very low power in the likelihood ratio test when alpha had values of -1, -0.8, and -0.5. And the reason why that comes about is probably linked with having common factors in the true model. So that the true model we could write as yt1 minus delta L is equal to 1 plus alpha L to epsilon t. And we would have common factors, totally redundant factors, if in fact alpha was equal to minus delta. If alpha is equal to minus delta, then we're saying that yt is in fact white noise. It's just epsilon. And what's happening in this range of the parameter space is that alpha delta is negative, so that alpha and delta are of opposite sign. And whenever the absolute value of delta is close to the absolute value of alpha, then the result is that the likelihood ratio test statistic has got low power. And that's arising because when these two conditions are satisfied, this is very close to having a common factor. And so it's very difficult to identify both delta and alpha.
Excuse me, how could the true model have a common factor?
Oh, well, a limiting case. I mean, at this stage we're saying the true model is in fact that. If that. But that point does lead me into what I was next going to say, that do we need to get too worried about this particular result? I think the answer is no, we don't, because I should emphasize again that although it was cast in terms of this model being the true one, in practice we're not looking for the true one. We're looking for a good representation of the process that's generating the data. And this particular finding that we wouldn't be able to distinguish this model, the first order autoregressive model, from an ARMA 1-1 model in these ranges of the parameter space, in effect is saying that when delta and alpha have these values, this model is likely to give us as good a representation of the process generating the data as this true one. So the fact that we can't, on the basis of the diagnostic checking, distinguish between those two models for that range of the parameter space needn't worry us too much. But as a consequence of that discussion, what we have to recognize is that it is in practice very difficult to uniquely identify values for variables like P and Q. And the situation in practice is likely to be one where alternative values of P and Q are going to give us almost equally acceptable representations of the process generating the data. And so there might be quite a wide range of models which are acceptable. Well, those are some of the problems that can arise with the univariate ARMA model. If you generalize that and go to transfer function type models, and all I mean currently by that is that we now introduce some other explanatory variables so that we can have phi of t yt related to psi of L zt, and then the moving average error process. Well, in this situation, even more problems arise than in the univariate case. And in particular, if we were to apply differencing filters to yt and to zt before attempting to find a model of this type, so that, let's say, we now difference yt until it seems to be a stationary variable. We also difference zt until that appears to be a stationary variable. And this could arise especially if yt and zt had seasonal components, so that the differencing might just be some seasonal adjustment filter. Then if we've done that, it's quite likely that the filters we've applied to yt differ from those we've applied to zt. As soon as that happens, even if the true model does relate yt to zt, if we've applied different filters to yt and zt, it could be very difficult for us to find this underlying relationship between y and z. If we'd applied the same filters to both, then that's common factors across here, not going through into the error term, but across here, and it's still quite likely that we will find this true relationship between y and t. But as soon as the filters that are applied to yt and zt are different, then even if there is an underlying relationship between yt and zt, it can be very difficult to find it. So that if we started modeling the relationship between the filtered y and the filtered z, we may not get anything at all like that if that were the true model. The second point is that, among others, Granger and Newbold have argued strongly that, especially for economic time series which have large trend components, it's very easy to get nonsense or spurious regression results. In other words, we just arbitrarily almost took the dependent variable yt, which had a very strong trend, and an explanatory variable zt, which also had a very strong trend, and performed a linear regression of the relationship between them. It's almost certain that we'll get a very high R squared, and probably the coefficient of zt would be highly significant. And yet, there need not be any really systematic relationship between yt and zt. All that's happened is they both have very strong trend components, and that's what we've captured in the model. And so results like that are said to be nonsense regression results, or just spurious regression. Because of that problem, they argue that it's a good idea to take the first differences of the trending variables and then only relate the differences. So perform regressions between the difference of y and the difference of z, and see if you can find any relationship between those two. Well, this could be appropriate in some situations, but notice that if these variables have been chosen for some strong economic reason, we do now get the argument that if we're modeling the difference of yt as being proportional to the difference of zt, and then say just a random error term, this model doesn't have a long-run equilibrium solution for yt other than 0. So that it's uninformative about equilibrium, and since economic theory usually gives us most information about equilibrium behavior, not disequilibrium behavior, a model of this type gives us less scope for using restrictions derived from economic theory. It also means that if we interpret this model now as an adjustment model, that in the short run, when we're out of equilibrium, this delta yt is our adjustment in the tth period to the change in the independent variable zt. The rate of adjustment is independent of previous disequilibrium levels. So that if in the previous period we'd only just been away from equilibrium, we would react in just the same way in this period as if in the previous period we'd been a very long way out of equilibrium. And both of those problems can be removed by introducing the levels of yt minus 1 and zt minus 1 in some form. And I want to follow this particular argument further in the next lecture in the application to estimating models of consumer durables in Canada. Well, those are two of the major problems that can arise with transfer function modeling. What I now want to do is to go back to the class of models that I specified at the beginning, and to look at one or two procedures for determining the orders of lags in these models. When epsilon t is a white noise error process, the autoregressive polynomial beta of L is of order p. The polynomials in gamma of L are of maximal order q. The autoregressive error process is of order r, and the moving average component is of order nu. And so empirically we want to determine p, q, r, and nu, and within the q we might want to allow the lags on each of the k explanatory variables in the vector zt to have different lag, and we may want to determine those qi's as well, when q is just the maximal value of qi. I want to condense the notation and write the first equation as alpha of L xt is equal to ut, when alpha of L transpose is in fact equal to beta of L minus gamma of L transpose. And x is correspondingly the partition including y and z. Now, even if we assume that we've modeled the systematic part of the model, the systematic dynamics, correctly, and we've chosen all the relevant variables to go in X, and we've got the orders of dynamics in the alpha of L vector of polynomials correct. So even if we've got that correct, we can only expect the data to give information about W of L, which is the ratio of mu of L to rho of L. And the data is unlikely to give us too much discriminatory power in determining the orders of mu and rho. It's likely to give us information about this as a whole, and much less information about the values of nu and r. Putting that another way, if we were to reduce the value of nu but increase the value of r, we're quite likely to get just as good a representation in terms of goodness of fit or value of the likelihood function as we had before. So that there are a range of values of nu and r which will be equally acceptable. That arises even though we may have come to this representation, this rational lag representation, from an original specification which was in terms of W of L. And we may originally have had a belief that W of L was of infinite order, and so use this rational approximation. But even if we're in that situation, the data is only likely to give us information directly about W of L and be much less powerful in determining nu and r. And indeed, if we refer to the simulation results of Hendry and Trivedi in the Review of Economic Studies in 1972, what they found in a Monte Carlo study was that it's the order of process which is important, rather than the form. And the form we mean either autoregressive or moving average, or a combination of the two. So that if you've got the order of dynamics correct, you're unlikely to have serious consequences if you've got the form incorrect. So that from this point onwards, I want to recognize that as a problem, and that we're unlikely to be able to derive procedures which will be powerful in determining nu and r separately. And unless you have very strong prior information telling you that nu is greater than 0, assume that the moving average component is 0. And the reason for doing that is just to recognize this problem, to say that it will be difficult to determine both of them. Therefore, we want to impose some arbitrary restriction to ensure that we determine the other. And noting that to estimate models with moving average error processes is more complicated computationally than it is to estimate models with autoregressive error processes, and therefore to concentrate on determining R when we've assumed nu to be 0. With the proviso that if you've strong reason, or if you've any reason at all, from economic theory, for example, to believe that the error process is moving average, then you take a different approach and allow for that moving average error process. So that we now concentrate on models of that type, where the error process is now only autoregressive. And the order of autoregression is R, and we'll now denote the maximal lag in the vector of polynomials alpha by L. when L now must be the max of P and Q in the previous formulation. Well, we can contrast the first model with a completely unrestricted model where we just have theta of L, a vector of polynomials operating on xt equal to some error process, which is assumed to be white noise. And we could, from that representation, relax those autoregressive restrictions and write that model in this form when if the maximal order of theta of L we denote as m, then m would be equal to R plus L. So that the first model is the second model with autoregressive restrictions. And we can write those in this form. And so our problem is now one of determining empirically the orders of aerodynamics, which are autoregressive errors, and systematic dynamics, which are the lags in alpha of L. We could equivalently say that that problem is one of determining the order of dynamics, which is m, and then we want to break that order of dynamics into aerodynamics and systematic dynamics. In other words, we then want to, say, determine the aerodynamics R. Once we've done the determination of the order of dynamics as a whole and determined the aerodynamics, that immediately tells us what L must be. And it's the second way of looking at the problem that leads to a two-stage sequential procedure for determining the lags in the model. Well, whichever way we look at the problem, that of determining the lags in the model, we come across hypothesis testing problems in that we have a lack of unique ordering of the hypotheses, and for some situations we have a lack of nesting as well. And what I want to do is, first of all, only to consider first-order dynamics, in other words, one-period lags in all variables as the maximum number of lags, and to look at the structure of the problem for that simple case. And I now have to introduce some notation. And the maintained hypothesis of first-order dynamics is now equivalent to first-order systematic dynamics, in other words, one-period lags in both y and the variable z, but zero-order autoregression in the errors. Another possibility for a model which has one-period lags in all variables is that we have no systematic dynamics. In other words, L in the previous notation is 0, but we have lags of y and z included in the model because of a first-order autoregressive error process. Another model would be one where we've got no dynamics at all. L is 0 and R is 0. An intermediate between those three, we can have two other models. Which are first order systematic dynamics in Y. In other words, yt minus 1 is included in the model, but zt minus 1 isn't. And there are no autoregressive error terms. Alternatively, we include zt minus 1, but not yt minus 1, and there isn't an autoregressive error process. Each of those is a special case of the most general model, which is one period lags unrestricted in both y and z. And for this model, if we then were able to reject the one period lag on y, we would get through to no dynamics at all. So we can move from that one directly to zero dynamics. And similarly, we can move from that to zero dynamics. It's also possible to perform a direct test of first order dynamics against zero dynamics. Everything above the horizontal line has at least a one period lag in some variable. So we can say that that's first order dynamics. Everything below the line is just the one equation, which is the static equation. And we have now the essence of the problem that arises, even in this very simple case, of only one period lags. And that is, when we consider the model with one period lags with no restriction at all, that's our maintained hypothesis. The most restricted model is the static model with no lags. If we want to test that static model against the one with one period lags unrestricted, we can, denoted by this arrow, we can perform a direct test of that hypothesis. But there are many other ways we can go through this array of hypotheses to get from the unrestricted hypothesis to the most restricted. And because there isn't a unique ordering of the hypotheses, we don't have the optimal sequential testing procedure to allow us to go through this sequence of hypotheses until we come to a significant test and choose the preferred representation. Preferred representation. So that we see in this diagram we have a lack of ordering, and so immediately we know that we can't use the optimal sequential testing procedure. But if we go back one stage and now consider two cases of first order dynamics, and case one, we'll say that for some reason, either because of the result of previous testing or from prior economic information, we know that the order of dynamics in the model is 1, so that in some form there are going to be one period lags, and there's no possibility of the static model being the appropriate one. So we're now restricting ourselves to be above the horizontal line. Well, in fact, in this case, we do have a uniquely ordered nest. In fact, the nest is very straightforward, and it consists of those two hypotheses, insofar as we're looking for an autoregressive representation. Because if either of these two hypotheses is correct, then there can't be an autoregressive representation. Because if you've only got a lag on y, then we know, because you haven't got the lag on z, we can't have an autoregressive error process generating that first order dynamics. So that insofar as testing for the order of autoregression, when we're in the case where we know that the order of dynamics is 1, these are the only two relevant models, and so the testing is straightforward. And what are the forms of the models? Well, for 1D YZ0 AR, we would have YT plus theta 11 YT minus 1 plus theta 2 0 into ZT plus theta 2 1 star transpose into ZT minus 1 star is equal to error term VT. So we just have YT regressed on YT minus 1, all the variables ZT. The star is now introduced to denote the fact that if any of the variables in ZT are redundant when lagged, for example a constant term, it's just the same currently and a 1 period lag, so we don't include it in both sets. So that ZT minus 1 star is the non-redundant variables at T minus 1. That is the unrestricted model. Compare that with the model with first order dynamics generated by a first order autoregressive error process, which would have YT minus rho 1 YT minus 1 minus gamma naught transpose ZT plus rho 1 gamma naught star transpose ZT minus 1 star is equal to epsilon t. And that's just the model you would have for a simple linear regression with first order autoregressive error process. And so we would test these autoregressive restrictions either using a likelihood ratio test or a Wald test in the usual way. So that for this particular case, the situation is in fact quite simple. And you do the direct test of the autoregressive restrictions. If you reject the autoregressive restrictions, then you might go back in this tree representation and now consider that although you know there isn't an autoregressive error process, there is 1 period lags, at least in some variables, but it may be that it's not in all, so that you would then test whether in fact the dynamics is only in Y, or perhaps in a subset of the Zs, but not in Y. And that could be done easily by using asymptotic T or F tests. The more difficult case arises when we specify that the maintained maximum value for dynamics, or the maintained maximum value of lags, is 1. But now we've got the possibility that we're going to determine our value of dynamics to be either 0 or 1. Which now means that this model, the static model, is a possibility. And so we aren't uniquely ordered. Anymore. And we could think of a number of testing procedures. A first one would be to consider the maintained model go from that to all the dynamics being represented by the autoregressive error process. And if that is accepted, test whether the serial correlation coefficient in the error process is significantly different from 0. So if you accept this model relative to the unrestricted, you've said that there's a first-order autoregressive error process. You can now test whether row 1 is significantly different from 0 or not. If it isn't, you've got through to the static model. And so that's an ordered sequence of moving from the most general model to the most restricted. And you're going through that route in the diagram. But we could perform the direct test of 1D 0AR with 0D 0AR, the static model. So that would be a direct test. And that corresponds to going through that route in the diagram. Well, from just inspection of the diagram, you see the remaining two possibilities. We can go down to exclude ZT. If we do accept this hypothesis so that the ZT minus 1 isn't in the model, we can go on to test whether in fact YT minus 1 is. If it isn't, we've got through to the static model. And in just the same way, we can test whether YT minus 1 should be in the model. If it isn't, we can then test whether ZT minus 1 should be, and if that isn't, we've got to the static model, which gives us another two routes of getting through the diagram. The question then is, do we use Anderson's optimal sequential testing procedure within each of those ordered nests, which would be a possibility, come up with a preferred model from each, and then attempt to discriminate between the preferred models? Well, the answer there in this context has got to be no, because this is only first order lags, and we've already had 4 nests for that possibility. So that as soon as the order of dynamics becomes any reasonable number like 4 or 5, then the number of possible orderings becomes very, very large indeed, so that computationally you would want to reject that approach. But also statistically, you're going to have so little power to a procedure of that type that you wouldn't want to consider it, because there'd be far too many significance tests. So if we're not going to do that, we must impose some structure on the problem. And one possibility is that we rule out from the beginning the possibility of doing the direct test. For the reasons I mentioned a number of lectures previously, that if we do the direct test and we reject this most restricted model, then we're still left with the problem of whether any of the intermediate hypotheses are acceptable. So that if we can find another procedure which considers the intermediate ones before getting through to the most restricted, they are in general going to be preferable procedures, so that we can rule out the second procedure. And that leaves us with this ordering as being a feasible procedure for the first order dynamics case. So that we would probably in first order dynamics use that approach and perform the test of significance in that sequence of ordered hypotheses. Namely, test for first order autoregression. If you accept that, then test whether the row 1 is significantly different from 0. And in fact, that would then give you a powerful test of the static model relative to the first order dynamics model. Well, those are the essential problems that arise in general. What I now want to do is to look at the second order dynamics case, which is more complicated. and you can, by simple extension in your own mind, generalize that to any higher order to see the complexity of the problem. And by second order dynamics, we mean 2D YZ zero autoregression. Across here we can have the whole of the dynamics being generated by a second order autoregressive error process. I have first order systematic dynamics together with a first order autoregressive error process. It's going to be better to write that in the middle, actually. So that's still second order lags in the model. We can have first order systematic dynamics and zero order autoregression. We can have zero order systematic dynamics, first order autoregression. And both of those models are now in the region of only first order lags in the model, or first order dynamics. Everything above the line has got second order lags. And then right at the bottom we can have the static model with no lags at all. Intermediate between all of these models, we can include models which have lags on Y but not on Z but not on Y. I don't want to put those in at the moment. It just makes the diagram even more cluttered. So that we have exactly the same problem as in the first order dynamics case, but now we have even more routes in getting from the most general model to the most restricted. And there are two procedures that we want to consider. One is that we assume or test first whether the whole of the dynamics is in fact as a result of autoregression. If we accept that the whole of the dynamics is caused by a second order autoregressive error process, then we've got the possibilities that the two routes in that process generating the second order autoregression might not be significantly different from zero. So that if we do accept that, we're accepting that the theta of L polynomial in the general model has two common factors, but those common factors could correspond to zero roots. And we can test that by, first of all, seeing whether we can now accept a model with only first order autoregression relative to the one with second order. If we do accept this, then we're saying that one of those common factors we pulled out at the first stage was in fact zero. And then if we accept that, we can test this model relative to the static one, which is now testing whether the second root is also zero. And that forms an ordered sequence. The other possibility is that we adopt a two-stage procedure which follows from the previous discussion. And the first stage is determine the order of dynamics, M hat. Second stage, conditional on R plus L hat being equal to that order of dynamics, determine R. Which of course means you determine L hat as well. And in terms of the diagram, that means we want to compare, in the determination of the order of dynamics, only models which don't have autoregressive representations or autoregressive error processes. And those models are the unrestricted model of second-order systematic dynamics, the model with first-order systematic dynamics, and the model with no systematic dynamics. So that we want to compare those three models. These three models form a uniquely ordered sequence of hypotheses. And we can test first-order systematic dynamics relative to second-order systematic dynamics by doing a simultaneous significance test on all the coefficients of variables at t-2. If they're not significantly different from 0, we accept first-order dynamics. And similarly, we can test first-order dynamics against zero-order dynamics by doing a joint significance test on all the coefficients of variables at t-1. So that for this first stage, we have a uniquely ordered sequence of hypotheses, and we can use the optimal Anderson sequential testing procedure. So that we have a uniformly most powerful solution to this subproblem for a given probability of type 1 error. What we then do is, having determined M, we want to factor that into R and L. Well, clearly, if the value of M was 0, we immediately know that both R and L are 0. If the value of M was 1, then the possibilities are only that that set of one-period lags was caused by a first-order autoregression. So that if we come to this model, because M hat was determined to be 1, we now move horizontally across and test the first-order autoregression model against this unrestricted, and choose one of those. If in fact M hat had been determined to be 2, then what is the best route to follow in testing second-order autoregression and first-order autoregression with first-order dynamics? Well, in fact, the optimal route to follow is first to test whether there is a first-order autoregressive error process maintaining the other lagging variables. So that's just imposing one set of autoregressive restrictions. If you don't reject that, you can then test whether you can impose the second set of autoregressive restrictions. And that corresponds to hypotheses which we can set up in this form, that we've, in the first stage, determined the order of the theta of L polynomials, and that order is M hat. What we now want to do is to determine R hat when the order of alpha must be M hat minus R hat. And so we're looking for that factorization. And we know that this, again, is a uniquely ordered sequence of hypotheses. And if we want to test those using the optimal Anderson procedure, we should move from the least restricted model, successively increasing the order of restrictiveness. Well, the least restricted model in that context is in fact the model where theta of L is identically equal to alpha of L, for both of order M hat. And we can see that either because we haven't pulled out any autoregressive common factors, or alternatively by noting that the rho of L is a scalar polynomial, common to all the polynomials in the vector of polynomials alpha of L. So that if there are no restrictions, this is the unrestricted model, and that's the least restricted. The most restricted would be that theta of L of order m hat is equal to R of L of order m hat into alpha 0. And so we test for those common factors, assuming first of all R is 1, 0, 1, 2, through to the maximum value, which of course is m hat. And in the second order dynamics case, that corresponds to this root. Well, to conclude the lecture this week, I just want to make a few final comments on that procedure. The first one is that we can't show that that procedure is uniformly most powerful. And that's a common situation when we have composite hypotheses. Namely, this static model is a composite hypothesis relative to the second order dynamics model. And the reason why it isn't uniformly most powerful is not difficult to see, in that in the two-stage procedure we've partitioned the overall problem into two sub-problems. The first one, determine the order of dynamics. And for that we can use a uniformly most powerful testing procedure if we determine the lags for all variables in xt simultaneously. If we allow the lags on different variables in xt to be different, then the situation again is different, and the determination of m hat as a whole is not then uniformly most powerful. All we can say at that stage is that if we determine the lag on any individual variable, the procedure we can use for that can be uniformly most powerful. But because in determining the lag on any one variable, the results of that are not independent of what we assume about the other variables, we can't argue that the testing as a whole is uniformly most powerful. However, if we restrict ourselves to the case where we determine the lag m hat, which is common to all variables in xt, this first stage is uniformly most powerful. When we come to the second stage, because of the structure of the hypotheses, which are uniquely ordered when r hat goes through from 0 to m hat, we can again find a uniformly most powerful test for that sequence of hypotheses. But the point is that we're testing these conditional on the value we've determined at the previous stage for m hat. So that in the first stage we've made a mistake on m hat, this no longer is going to give us the appropriate result. And it's because the second stage proceeds conditional on the results of the first that when we put the two stages together, we can't argue that the two-stage procedure is a uniformly most powerful testing procedure. And in particular, we can think of examples where this procedure is going to have low power. And this would be against alternatives which have higher orders of dynamics, but those higher orders of dynamics are caused by higher orders of autoregressive error processes. And the reason why at this first stage we weren't able to pick up that higher order of dynamics was because of the multicollinearity between the large number of lag values unrestricted in all variables. Whereas if we'd imposed an autoregressive restriction on those variables, we would have got through to the higher value of m hat. So that's one particular case where this procedure has low power, and there are other cases. So that the argument in favour of this procedure is that it seems reasonable on the grounds that it seems logically prior that we should determine the order of dynamics before we go on to see how that dynamics can be factored into error components and systematic dynamic components. And that's the argument in favour of the procedure, together with the fact that we can use tests of misspecification to supplement the two-stage procedure to check that we've taken the right decision at each of the two stages. But I'll discuss that briefly at the beginning of the next lecture when I'll show you an example of how we can use this two-stage procedure.